All right. Whoa, that's a lot of explicit content. Today, we're learning to differentiate implicit relationships. We'll be successful when we can find implicit derivatives. All right. So we have the same equation written two different ways, right? Exact same equation written two different ways. One is explicit, the other is implicit. Which one's which? Take a moment. Think about it. Let me know which one you think. Let's try something a little different. Now that you've thought about it for a moment, there's 7 of you. Here's what I'm going to do is I'm going to randomly pick one of you. I want you to unmute and tell me what you think. Which one is explicit, which one's implicit. And again, it doesn't matter to me if you're right or wrong. I'm just looking for an option. So let's find out who it's going to be. And this is by alphabetically by first name, just so you know. That's number 6. Savannah, if you would kindly tell me, which one do you think is explicit? Which one do you think is implicit? Oh, you're in the car. Can you unmute it all?
Sorry, I had to take my sister to a dentist appointment.
Oh, fair.
So I'm like almost home. I'm like 2 minutes away.
Oh, okay. Never mind. I'll pick someone else while you're still there. My bad. Here, we'll run it again.
Okay.
That's a really good reason not to do that right now. 2, Emma. Why don't you tell me which one you think is implicit, which one's explicit?
The first one is implicit.
All right. Great guess. The first one is explicit. So thank you so much for being brave and giving me an answer. I appreciate that. And that's part of the reason that I want to spend the time talking about this, because sometimes like those words explicit and implicit, we're not super clear. Like we kind of use them a little bit up in before calculus, but we don't use it a whole lot. It's definitely been mentioned to you, but we don't just use that language a lot. So this first one is explicit because the equation is solved for one variable. It's like y equals x equals. Most of the time, those are the relationships. I mean, most equations and relationships you know of are set up that way, right? They're set up explicitly. Not all the time, but a lot of the time. So the thing is we can differentiate the explicit one. We have a rule for that. Like we could rewrite that as x to the negative first, then use the power rule, and y prime should be -1 times x to the negative second. Or you could rewrite that as -1 over x squared. So we could do that. But how would I differentiate the one on the right without rewriting it? That's a question. And that's what we're going to explore today. Because we can. And since these are the exact same thing, we should get the exact same answer. So we got to figure out how that's going to work. So how are we going to do that? Are we going to use sorcery? No. Magic? Nah. Definitely some treats. It's October, right? Nope. Tricks? Oh, no, it's not tricks. Implicit differentiation? Oh, yeah. I spent like 5 minutes making the animation work in that for the record. So I hope you appreciate it. If you don't, well, I still had fun doing it. So I'm going to go with that. So the idea here with implicit differentiation, we're going to take the derivative with respect to a particular variable. And what I mean by that is that every other variable then is going to be assumed to be a function of that variable. So like when we were using for chain rule, when we were using u to rewrite something, we basically assumed u was a function of x. So then you do the derivative and then multiply by the derivative of u, which was u prime, which we didn't always know what it was. I mean, we always knew what it was because we defined it. But with implicit differentiation, that's the kind of the big idea here, is every other variable is going to be assumed to be a function of the variable we're taking a derivative with respect to. This is the meme that I had in there from the previous times, but I feel like it's a little less funny during COVID. So I wanted to make light of it in a couple ways. So there we are. So I want to talk about the difference of these, because when we first looked at these, I'm like, technically there's a difference, but I want to talk about that there is an exact difference. So which is which, and what do they mean? Well, let's look at dy over dx first. Fun fact, we're going to do a little language and parts of speech. Dy dx, it's a noun. It's an object, is what a noun is. What dy over dx is, that is the derivative of y with respect to x. Now, before I go much further, when I say with respect to x, another way to think about that is it's like how y changes as x changes. So that's what it means when I say the derivative of y with respect to x. It's like, how does y change as x changes? All right. So again, the derivative is set up intentionally in the way we built it up, pun intended, derived it. It is slope. It's just slope at a single point. Now, again, dy dx is the derivative of y with respect to x and then whatever it is, but it's an object. Again, coming back to our parts of speech here, d over dx, what's that? That is a verb, which means we're taking an action. We're going to take the derivative with respect to x. So if you remember back to 2.1, when we first looked at those derivatives, there are several different ways we could write it out. And one of the ways was like d over dx of something in brackets, or I think it was in brackets. That's because that was pointing out we're doing this action on this thing. Dy over dx is saying this is the derivative of y with respect to x. So like this is normally an object that we're dealing with, as in the action has already been taken and there's an object now. Whereas d over dx is like, hey, you need to do an action. Do this action. This is an action to be done. Verb, 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 verb. So this is the thing we're going to focus on. Again, it's the idea to take the derivative with respect to x is to find out how the relationship is changing given a change in x. Again, that sounds like slope because it is. Oh my. Now it doesn't have to be d over dx. It could be d over dt in this case, or literally any other variable. Literally. So let's press X to continue. All right, so let's look and see how this changes with these a couple different expressions. So this first thing is saying, let's take the derivative with respect to x of this thing in brackets. Well, that should be bring down the 3, multiply 2 by 3, so 6. Subtract 1 from the exponent, 6x squared. Boom. And again, these are the same variable. Nothing new. Nothing wildly crazy there. Down here, notice these aren't the same variable. We're still going to start the same way. Well, the derivative of this will be 3 times 2, 6. Subtract 1 from that to get y squared. But notice there's something extra. Because when we did the derivative here, it's with respect to x. That means y is some function of x. Remember when we did the chain rule, I talked about like u to the third. The derivative of u to the third with respect to x was 3u squared times u prime. So we need to put something else in there. And we're going to put dy over dx. Again, I don't know what dy dx is right now, but what I can say is that it should be multiplied by whatever dy dx is. Dy over dx. Again, this is an object. We don't know what that is, but we know that it should be there. Okay. dy over dx, because again, this wasn't the variable. Technically, we could have this up here as well, but if I have dx over dx, it's just 1. So we don't need to have it there. It's technically there, but it's unnecessary because it just simplifies to 1. Where dy over dx, again, is an object. I don't have to know what the object is. I just know that it's there, okay? And Shrek's there to remind us about the layers, remember from chain rule. All right. Based on those two that I just showed you, I'm gonna give you a minute. Now, let's try 30 seconds. On your own papers, I want you to try both of these, okay? Go. Uh, 10 more seconds. Or 5. I'm not really sure. I don't remember the time I started it. Oh, right there. Okay, so the first one, our result should be 1 plus 3 times dy over dx. Because if I'm taking the derivative of this whole thing, I can break it up and look at the derivative of each piece, right? Well, the derivative with respect to x of x is just 1. Because the derivative of x is just 1. And then be multiplied by dx over dx, which is just 1. Hey, right there. Well, 3y, the derivative of 3y would just be 3. But since we're doing the derivative with respect to x, we're also multiplying by the dy over dx because of the chain rule. Again, we're assuming that y is some function of x. And since it is, there's going to be some change that could happen there. Again, the dy dx, maybe that number is 0. Maybe there's another equation that goes, or expression that goes in there. We don't know, but we still need to include that. Notice down here, the difference between the first and the second one is that this was d over dx. This is d over dt. Notice the difference here. It's still, the derivative of x is still 1, but we're assuming x is a function of time, or t. Usually t represents time. But x is a function of t. So we have to do 1 times dx over dt. And for 3y, same thing, except instead of dy over dx, it's dy over dt. All right? Again, that's all from chain rule because we're assuming that each of these variables, if it's not whatever's down here, is a function of that variable, which means when you do the derivative, you're assuming that, I guess what I'm trying to say, and I don't think I was as clear as I was saying this. We're assuming that since y is a function of x, that we have a composed function and that we need to, when we do the derivative of it, make sure we apply the chain rule. And since we don't know what y is, we're just going to put in the object in each of these. We don't know the exact relationship between the variable we're taking the derivative of and with respect to what variable. Again, keep looking for those layers. Keep remembering that there's some composition going on. All right. So this one's kind of wild and crazy. Like I just threw this out there. Again, just random. So if we're to look at this part, and we'll just do this one together. I'm going to annotate as I go. Ooh, orange. Let's do that. So for this, I'm looking at this piece first. So looking at that piece, my derivative of that with respect to p is going to be 6x to the first. I see p and x are not the same thing. So I'm going to multiply by dx over dp because I'm assuming that this is a composed function, that it used to be 3 of something in parentheses with p in there. I don't know what that is. I'm just saying it's x. So I need to multiply by that. Well, let's go over here. Well, the derivative of cosine is negative sine of y. Now looking at the variable inside here, because it's a composed function, y is not the same as p. So I'm going to multiply by dy. That was a bad y. Looks like an m. Rip. That didn't help literally at all. Over dp. Now I'm going to turn off annotation and see if... Well, look at that. Same thing that I had on the slides. Let me turn on annotation so I can get rid of that so you can see. See? There it is. Again, I did plus negative sign there instead of just doing subtraction, but that's the idea. All right, so now that we have this, I want to come back and look at how finding the derivatives is going to work. So we know dy dx should be -1 over x squared, or -1 times x to the -2nd. Let's find out. So let's take the derivative of this with respect to x. Okay, so something crazy just happened here, and I want to point out what happened. We're assuming that every variable here is a function of x, right? Which really means I have x, which is a function, times y, which is also a function. So I had to use product rule here. This is results of product Hey, there we go. Writing's okay. This is a result of the product rule. Because again, if you think about it, derivative of x is 1. So 1 times y plus x times the derivative of y with respect to x. Again, that would just be 1. But then we have to multiply by dy dx because it's a composed function. All right. Now we're just going to try to solve for dy dx. So I'm going to subtract y, divide by x. That looks different. But we know what y is. If I divide both sides by x here, I get y is 1 over x. So I can substitute that in there. And if I simplify this complex fraction, I get -1 x squared. Clear. Oh, I still have annotation on. Woo! So again, whether we do implicit or explicit differentiation, it's fine. Now, in this one, looking at the process here, this seems a lot more complicated than doing the explicit derivative. You're right, it is. But that's not always the case. There are some times, in particular, if you're finding the derivative of something that isn't a function, implicit differentiation will help you so much more. I used to do an example with that. I felt like it never really worked out. It's later on, so you can check that out. But that's it. That's all what I have for you today. I just felt like we needed more Shrek in our lives. All right. Oh shoot, I never changed that. Do Monday? That's silly. No. Thought I changed that. Where is the things? It's due soon. So there's that. I'm just gonna. I know you're probably writing it down right now, so I'm gonna give you a hot sec. And give you about 20 more seconds to write down this assignment. Today's A-Day. Yeah. If I'm not super busy, and I don't anticipate being super busy, I'm gonna be in the Discord general chat for calc class probably around 3. That's my goal today. My plans to be in the Discord chat around 3 today. So if you want to come chat with me about calc or life or whatever, I should be there for about a half an hour later today. And just so you know, I have some post-credit scenes, which are just some extra problems I worked out. Here's finding dy dx given something that's not a function. Again, same thing. And then finding it at a point, which in this case, you have to plug in both x and y. This is finding the second derivative of something. And that's just pointing out which of those are functions and which aren't. So those are for your consumption. Several of those are also in the book. So that's what I have for you today, folks. Unless you have any immediate questions.